Okay, so the next terms we're going to talk about are half layer and attenuation, and we've already talked about attenuation a little bit. So that will just be kind of review. Half layer is similar to the concept of like half-lives when you talk about like carbon-14 dating and medications and things like that. The half layer is this point, it's the tissue depth where half of the initial output intensity has been lost. Okay, so as we go deeper, we expect that attenuation to happen, right? Expect us to lose some energy to the tissues. But depending on the settings we set, those depths are going to be a little bit different. Okay, so 1 watts per centimeter squared loses about 50% of its energy, somewhere around 2.3 centimeters. Okay, if we're talking about a 1 megahertz frequency. Okay, so now at that 2.3 centimeter depth, we're really only getting 0.5 watts per centimeter squared. If we increased that depth by doubling it, so now we're going to 4.6, we get about 0.25 watts per centimeter squared. So that's what the half layer means. Now, if we switch that to 3 megahertz, which we know is more superficial, we know we end up absorbing more of that energy earlier, the half-life depth is only about 0.8 centimeters. So we go from 1 watt per centimeter or 1 megahertz that can get us down to about 2.3 centimeters before it reaches this half layer value. 3 megahertz is only at about 0.8 centimeters, so much shorter. This takes into account any energy that is not reflected or absorbed ends up passing through to those underlying tissues. So again, this really takes into account the law of Griffiths-Draper that we talked about in our other modalities. So just to review that attenuation that we talked about a little bit already, right? That's this decreasing in energy intensity, so this losing steam. So the half layer is just the numerical value kind of showing that attenuation. And again, remember that that's due to absorption within the tissue or reflection or refraction of the wave as it goes deeper.